Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my science and math channel. Today we're going to be talking about science, physics, and it's called motion in two dimensions. But what we're really going to be talking about is throwing things off of a cliff. Things or throwing things in general, throwing balls, all that sort of stuff. Remember I told you in the last video that when I was your age, and was taking physics and chemistry and math, all these hard maths, that I had this just idea, this wrong idea, misinterpretation of that there was just an infinite number of word problems for my teacher to choose from. But really, there's a very small number of word problems that you just change. It's the same thing, you just change the situation a little bit or the numbers. But once you know how to do these certain little groups of math problems, that's what's going to be on the test. That's what you're going to be doing. So I told you about how there's just certain ones and that you just see them over and over and over again. And finally you get to be my age or smarter people way before, and you realize, oh, there's really not that many problems out there, that there's just certain ones you see often. So anyway, we're going to be talking about that. It's called Motion in Two Dimensions, and like the last chapter, the second video is going to probably be the longer one with the math. This one isn't as mathy, and so I'm real proud of y'all for coming back after all that trig and that math, because that was a lot of math. That was really advanced math. You can feel smart because you learned that math. All right, so now we're to chapter 7, and this is a class primarily made for homeschoolers using that book. But anybody who likes the way I explain things, you are more than welcome to be here. I'm Miss Lisa. I want you to like, share, and subscribe. I have a goal. Everybody has a goal. My goal is to get 1,000 subscribers so that I don't have to record then upload on YouTube, that I can do like I did last year on Facebook. And I used to do Facebook Live, but Facebook makes them go away after a while. And since I've returned to teaching public school, I need the videos to stay up for the homeschoolers, because I want to bless the homeschoolers with these videos and these classes for free. And but it would be nice if it was easier and it didn't take so much time. I like blessing the homeschoolers, but this has taken a lot of time. So far I've spent my whole fall break making videos for homeschoolers. So I'd like it to be easier. I just like to do it faster. I don't mind doing it. I just want to do it faster. So anyway, okay, so let's go back to our topic, motion in two dimensions. So what we're going to be talking about is projectile motion. That's what this is. So I drew a cannon shooting off. You'll have someone throwing a ball, someone shooting a gun. This is one part of school where you actually see guns, where, you know, usually no guns in school, no even drawing a gun, no making your finger like a gun. But when you get to physics, projectile motion, we are shooting those projectiles. So I teach in public school, and I don't teach physics right now. I'm teaching physical science and chemistry. But last week when I was there, they had Nerf guns, and they were shooting them down the hall in school. They were learning about projectile motion, just like you're going to do. So you might need to get out those Nerf guns and shoot them and enjoy it. It's fun. These are fun things. All right, so this is the first idea. So we are going to talk about a gun to start with. If I imagine I had a gun and I shot it, not at anyone, just safely, off into the horizon, and I shoot it in a place where the bullet's gonna fly until it finally just hits the ground. It's not gonna hit anything. So with my gun, I shoot it and off it goes, forever in the desert. Nobody's there. Nothing's gonna get hit. It just keeps going until finally the bullet I hold it straight out and I shoot the gun, and the bullet finally just, because of gravity, hits the ground. In my other hand, I have a bullet, and I hold it out, and at the same time I fire my gun, I drop the bullet, just straight down. Which one do you think will hit the ground first? You can and let me tell you, when you do your math videos, you should pause it and do it, and then watch me do it and check it and stuff like that. Feel free to pause. It'll help you learn on these videos. this is the weird thing, they will hit at the same time. Isn't that an amazing idea? It will be the same exact time. And this is why. And that's what I've got right here. Every motion, which we learned last time, we started talking about how those forces can be divided into their x and y component. You know, like on a graph, on the coordinate plane, the y goes up and down vertically and the x goes horizontally. And whenever you have motion, it will have an x component and a y component. And because I'm shooting my cannonball down off of a cliff, the y I drew down instead of out. But at each point, as this thing's going down, it has an x component and a y component. And this is the weird part. They are completely independent of each other. So it doesn't matter that I'm shooting the bullet out of my gun, that it will not affect the y component at all. The y component is only controlled by gravity, pulling on that bullet, and it will do it at the same amount because the acceleration due to gravity is a constant, 9.8 meters per second squared, and they're going to hit at the same time. So get that in your brain, and it will help you with all of these problems, is that these are independent. Your book says independence of motion in 2 dimensions, and that's what it's talking about. And for their picture, they dropped, it looks like a basketball, and threw a basketball, and then they took pictures, timed release camera. So, and you can see that the balls, even though one's going out, one's going down, that they're always at the same height, and that they hit at exactly the same time. So when you shoot this out, it's called a trajectory. And now sometimes your point of view changes what you think what's going on. Like, for example, if you were riding in a car and you're throwing up a ball and catching it again, it would look like the same thing if it was going constant speed. It would look like it was still, like you're just throwing it out and catching it, just the same as if you were doing it in your bedroom. But if you were standing on the road and you saw it, it wouldn't look like it was just going straight up and down. You would see it that it's moving, and it's going doo doo as it's going up and down. So when things are different because a point of view is called parallax. That's a fun word, isn't it? So sometimes we have to think about parallax. Another thing with parallax is that it can make things appear different than they are. So, like, for example, my son will be driving, and I'll look over at his speedometer or his gas gauge or whatever, and I'm like, oh, you're about to run out of gas. You better get some gas. He's like, no, Mom, I got a quarter tank. Because he's looking straight on it, and he can see it. I'm looking at a weird angle. It looks different to me. And in chemistry, when you're reading a graduated cylinder, you have to bring it up to eye level because we want to avoid parallax and we want to read our chemicals correctly, and you read it from the bottom of the meniscus. So that's a little free chemistry. That doesn't have anything to do with the physics except parallax. All right. So on page 135, we have our formula, which is how we, for x and y. And there's 2 different formulas for the x component and the y component. And I will be going through those as I go in the math video. If you look on page 137, you have someone hitting a golf ball, and you can see that the shape that it makes is a parabola. So for some of these problems, not in this chapter, but for some of these parabola trajectory problems, you end up using they're quadratics, and you end up using the quadratic equation. Now, something I didn't tell you last time, and I meant to, and I'd written it down, but I might, if I remember, I'll put it in the description of the last video, is that there are programs on your calculator that can help greatly with the quadratic equation, and even adding vectors. There is an app called SciTools, and on it is got, you go into it and there's a thing where it will actually do all that trig for you, and it will figure out all your vectors for you. My students last year discovered it, and they were like, yes, this is awesome. So if you don't have it, you can go to the TI-84 website, to Texas Instrument. You can get your parents to register as teachers because this is a homeschool class, so your parents are teachers, and then they can download programs and apps onto your computer, onto your TI-84 graphing calculator, which is a computer. So that is very helpful. But there's one for adding vectors. So anyway, in Algebra 2, we do these problems also. We do it with the quadratic equation and with the height equation. So this has a little bit of overlap. I think Algebra 2, I don't think we teach this in Algebra 1. I'm trying to remember. If you look on page 138, you can see a time-elapse picture of throwing a ball, and you can tell about what happens. So we're going to talk about it. Okay, so here's my ball. You have to pretend it's a ball. You got a ball and you throw it up. When you very first throw it up is going at the fastest it's going to go. It's got the most acceleration as it's in your hand, and then you let go of it, but it's going the greatest velocity, the greatest speed. But then as it goes up, it gets slower, 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 stops where it's not going up anymore, and then it starts going down, 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 down. And you can see in the time-lapse picture that there's more distance at the ends of our parabola because it's going faster, and less distance up at the top where it gets slower, slower, slower before it goes back down again. So that is, and we can talk about its kinetic energy. This kinetic energy is greatest, and then it's lower, and then it gets faster again. That its potential energy is low here, but its potential energy is high here, and its potential energy is low again at the ends. We did the lab last year, the softball throw. You can do that, but we didn't throw a softball. We threw a little blue bouncy ball we got at Walmart for $1. So you will be doing that, and we did all the math and stuff. That was fun. Now, periodic motion. Periodic means something that is repeating. And so the period is the time for one repeating thing. So it could be a pendulum swinging back and forth, and the pendulum is how much time it takes to swing. It could be something turning, and it would be the time for one revolution. Or it could be, and we talked about in this chapter, a spring going up and down, and how long it takes for it to get back where it started from. Each of those things is a period. And so we're going to be doing some math with that. One of the things we're going to calculate is centripetal acceleration, which is the change in velocity over the change in time. And we can also, so you'll come back for the math, and I'll show you how to do the calculations. Another thing that they put in this chapter is the idea of torque. Now, what is torque? My dad used to say, that torques my jaw, and I had no idea what I was talking about. Torque is a rotational force. So what I'm doing right here, making this like a handle going around, is torque. Okay, so when he said that torques my jaw, that means it's like a hit in the face, turning my face. Like it's like saying that's like a punch in the face. It's the same thing. That torques my jaw. It's probably a country expression because my dad was very country, from Franklin County, Royston, Georgia. But so that's what it's a rotational force, and where the formula for it is that torque is the force times the length of the lever arm or lever arm. If you say lever or lever, but this is a lever. If you remember physical science or middle school where you learned the 3 classes of levers, or if you say levers. In the South we say lever, but up north and on TV they say lever. So just to let you know, one time I said lever and someone thought I said lever. No, that's something completely different. That'd be biology class, not physics class. All right, so what does this mean? It means that it takes less effort the longer this distance is, the longer this length is. So imagine doorknobs. Doorknobs are on the very edge of the door. If the doorknob was over by the hinges, it would be very hard to open and close the door because that length wouldn't be long enough. But if it's a nice big door with the doorknob far on the side, it's very easy to open even a big heavy door. Another one is, like, say you've got a wrench and you're trying to turn a bolt and it won't go. they sell these things that are torque extenders, and you put them on the end of your wrench, and it makes the handle longer, and then it's very easy to turn that wrench. You have to be careful because you can very easily get too much force, too much torque, and it can mangle your bolt. So it's like, with great power comes great responsibility. Don't mangle the bolt with your knowledge of physics. So that's another one. So any handle, any rotational force, and you can even think about with a steering wheel. If you had a little steering wheel, it'd be harder to turn than a great big steering wheel would be easier. It's because we've extended that length of the lever arm, and we would increase our torque. So that's a simple machine. So simple harmonic motion, what they talk about the spring, harmonic meaning it's repeating, and it has a period, the time it takes, and it has an amplitude, which is how far that spring is stretching back and forth. And you can read through about where the potential energy is the greatest and the kinetic energy. Okay, and then they talk about the pendulums too, swinging back and forth like I did. My cat, for some reason, is yelling. It means she wants someone to play fetch with her. My cat plays fetch, and she's hollering because she wants someone to throw her mouse so she can bring it back. Do y'all have cats that play fetch? I do. They said my cats are related to Manx cats, the tailless cats, and they act more like dogs. They run to the door to greet you. They want to play fetch. They're just a little bit more social than regular cats. So I think they're great. I think Manx cats are great. Ours are actually Siamese Manx mixed. But some of them have tails and some are tailless, but they all have that real friendly, outgoing dog personality. So if you hear a cat hollering, you know what it is. She wants to play fetch. All right, so come back for part 2. Read your chapter, look through it all carefully. Come back for part 2 and we'll do the math. And that's the fun part, right? Because math is great, science is great. I'm Miss Lisa. Like, share, subscribe, and I'll see you for part 2.